I'm trying also, like the previous speakers, not to use the microphone. So is it okay? Yeah.
But please a bit louder.
So okay, I'll try my best. Now it's okay. Otherwise, I'll use the microphone. Please just indicate. So thanks, Maria, and thanks the organizers for the invitation to speak here, and in this beautiful place and its wonderful workshop. And maybe for me, it was the main purpose of the workshop is to learn, and I learned a lot here. So thanks to the speakers for that. This is going to be, I think that, surprisingly, the mention of the Dirac operator today is almost the first time. It is, but it will be a Dirac talk in some sense. It is a joint work with Tomio Umeda, who is here. Okay. So I'll consider first order systems. So a first order system is something that, as is written here, oops, sorry. Like this, so you are talking about K by K systems. These are matrices so that the operator is self-adjoint. And so these are, the coefficient matrices are all Hermitian over the complex numbers. And please note that I'm including a non-homogeneous term, so as, for example, to have the massive as well as the massless Dirac operator, for example. Okay, now here are the examples. A good part of classical physics actually is expressed in terms governed by such equations. And you have, of course, the electromagnetic, this is well known, but also acoustic, elastic waves in inhomogeneous and anisotropic media. And on the other hand, you have, of course, the Dirac equation, which was presented during this week. So much. Now, the purpose of this talk will be a relaxed talk because I know that I'm now between you and the evening freedoms, so I have to do. And but the purpose is actually to follow, in some sense, the philosophy of Courant and Hilbert, famous treatise, where they actually tried to put everything in the same basket. That is, to look at systems as they are, including the Dirac, explicitly the Dirac systems.
Sorry, I have a question. Why is M not Hermitian on the previous slide? Because if you make it Hermitian, the operator may be non-self-adjoint.
This is why I add the M0.
Yes,
the
but then you write M not is Hermitian.
Yes, that's right. It's
you see, I agree that M1, M2, Mn are Hermitian.
Yes, and the overall, that is M0 should not be Hermitian. M0 absorbs all the rest, if I write it like that. Normally we write it otherwise, like divergence type. Okay, you're right. I chose, in the sense of history, to bring three exemplary citations of things that existed for this topic. The first is a classical work by Wilcox on asymptotic wave functions and energy distributions in strongly propagative anisotropic media. To be explained, what are the terms here. But this is a very classical using eigenfunctions and the old classical style of Titchmarsh or Berezanski to deal with such systems. The second is already limiting absorption principle to be explained, but using eigenfunctions by Ricardo Weder, analyticity of the scattering matrix, wave propagation in crystals, again for what is called strongly propagative systems. And the last one is a fairly recent study on curvature properties of the slowness surface of the system of crystal acoustics for cubic crystals in the Osaka journal, recent by Otto Lies. And as you'll see in this talk, they represent various stages and various problems in dealing with these systems. At this point, I make a disclaimer that is, you see, the last one represents the good part of Fourier integral operators where exact detailed information leading to geometric optics is needed. So all the singular points of surfaces to be shown appear, and then you have to study case by case almost. What I'm trying to do is exactly the opposite, to give a robust treatment and presentation. Okay, so Dirac operator, I put this slide, but I don't think that anybody needs it. Only that I denote by HM the Dirac operator. So the rest is, of course, known. Problems, as was mentioned, the spectrum extends over -infinity to infinity with gaps, so it is not elliptic, and we still want to apply, this is sort of a code word, something like Schrödinger methods, by which I mean mostly spectral theory, as you'll see. And here, the explanation for that is the fact that has been used heavily here, that the square of HM happens to be, of course, the minus Laplacian plus m squared, and most of the treatments were done using this fact. Okay, so, which brings it back in this particular case to an elliptic treatment, in some sense. Even though HM is not the official, this is a self-adjoint operator, of course, but HM is not the official square root in the formal sense of this operator because it is not a positive square root. Okay, so let me specialize first to the case of the Dirac operator. You have the symbol, which is HM, acting on in Fourier space. Xi is for me the Fourier coordinates throughout the talk, so you have the symbol. And the eigenvalues of HM Xi are exactly these two, each of double multiplicity, except for the case, the messless case at Xi equals 0. Now, for nxc, you can have a unitary matrix umxc, which diagonalizes hmxc, as usual, because it's Hermitian. So this is umxc, and the next one, you see, if you take now the Fourier representation, and you take G here as the transformation that multiplies every xc at every xc by umxc, you get a unitary, of course, transformation on the L2 space, and which diagonalizes the whole of HM, of course, and this is known as the Foldy-Wood-Huizen-Tani. The last time that I say this, I'll say FWT transformation, and of course, then you have once you have this diagonalization, you can have the spectral family, and the spectral family, if you take lambda bigger than 0, for example, and you take a nice f, say, this is my notation, too late, but you see, this is my notation for function defined on R3 and valued in C4 as usual. Okay, so EM lambda FF, that is the L2 product for this spectral projection, is exactly this. Please keep it in mind, I'll use it later on. So it is a very simple expression for the spectral measure. For that. Okay, this transformation, by the way, was heavily studied in detail, and in this talk you will see that actually you don't need to study it in precise detail, what are the behaviors with respect to Xi and so on. This is one message. Back to general systems now. So we are talking about this L. So L is a perturbation of a constant coefficient symmetric operator. Now, these are all of them are Hermitian, constant Hermitian matrices. So, and we regard L as a perturbation, in a sense, not to be specified exactly today, of this constant coefficient symmetric operator, Hermitian operator. Okay, here are some definitions. So, the first one is about, I take the homogeneous part, that is, if you wish, the leading part or the principal symbol or whatever. We say that it is strongly propagative if this symbol has a kernel of fixed dimension, D, independent of Xi. I mean, D is independent of Xi. The kernel depends on Xi, but the dimension is not. So this is a definition. And then has a kernel which is independent of Xi, and then you have negative and positive eigenvalues of m of xi for every xi different than 0. They are, first of all, equally numbered, positive homogeneous of degree 1. And if you look at the discriminant of mxi, the z, that is the set of bad points where actually you have what leads to caustics and all those things. It's z is a closed cone of Lebesgue measure 0, and every eigenvalue of mxi has constant multiplicity in Rn minus that. So you have a cone of bad points. By homogeneity, it's a cone, it's a straight cone. And outside of this, every eigenvalue really has. And I denote all these eigenvalues, distinct eigenvalues like that. They are equally numbered, as I said, and they have all kinds of properties, simple properties. All of them have been used, all these properties. That is that it's real analytic where it is nice, and it is homogeneous, positive homogeneous of degree 1. There is a more restricted class for operators where actually you don't allow such degeneracies leading to caustics in geometric optics. Since this is called a uniformly propagative system, that it is strongly propagative, and moreover, the eigenspace associated with every eigenvalue has constant dimension. That is, there is never degeneracy at singular points, no cone like that at singular points. Okay, once we have this, either that for uniformly propagative or strongly propagative, the surfaces, these surfaces, lambda jxc equal to plus or minus 1, two sides, are called slowness surfaces of the system, as appeared in the title of one of the articles that I showed you. And of course, a study for Fourier integral operators, the study of slowness surfaces is an essential thing. And you really go for, the game is to go for the singular points, which we are trying to avoid here. In Courant Hilbert, they are already well known, and they are called normal surfaces. They are related, they are polar to characteristic surfaces. Okay, now let's take the symbol of the non-homogeneous system. So now we add the sub-principle M00, so we have this. Homogeneity is now gone, and we have to replace it and still have those surfaces of eigenvalues. What I'm saying is that here's a proposition. There exists a closed set Z tilde in Rn, Lebesgue measure 0, such that for every xi there, every eigenvalue of m tilde, we are still assuming that it is strongly propagative. So no question the kernel exists, but it is of uniform, of constant strength. So every eigenvalue of m tilde xi, that is not an eigenvalue of m00, it is not pushed by m00, has constant multiplicity, but we are losing parts of the minus of the symmetry properties of lambda jxc. We don't have them. And there are orthogonal projections like that for the eigenvalues. Okay. So if I want to state some more properties, so I take this symbol and we denote by, for every matrix K by K Hermitian, we denote by S lambda A, the spectral subspace, that is the subspace of vectors lying below lambda in the spectral representation. And so, and then I define an open set U lambda for in the xi space. It's an open set of all those values for which that symbol has something in it. That is that S lambda is not empty. There is a spectral subspace below lambda for that xi. Here's a proposition. There exists a finite set, lambda in R, a finite set of points, and an integer valued function k lambda for all those lambdas in intervals separated by lambda points, so that k lambda is constant in open intervals. And for k lambda bigger than 0, this sets the surfaces, sort of, the surfaces, equisurfaces for the eigenvalues away from Z tilde are bounded smooth n-1 dimensional manifolds, and the others above k lambda are actually empty. So you have, for each interval, you have a k lambda which is constant in such interval, where you have so many eigenvalues with fixed multiplicity away from Z tilde. The proof of this is an exercise in algebra and geometry. You know this kind of thing. It's a semi-algebraic set with measure 0 to get from SAD, and so it becomes, it's a Tarski-Seidenberg. Here's another proposition in this. So these are all kinds of structural things. You take lambda in one of those nice intervals away from the critical values, so to speak, the big lambda, and you take such that k lambda bigger than 0. So you are actually talking, I mean, if k lambda is equal to 0, this, you can think of the gap between minus m and m for the Dirac case. So, and then we can take this u lambda, the collection of the open set in Rn where you have something in the spectral subspace below lambda. It exists, it contains, consists of a union of uj lambda, so that the boundaries away from the singular set, the boundaries are exactly the gamma j lambda, the equisurfaces for the lambda jxc, the eigenvalues. And of course, uj lambda is lambda j c less than lambda for all those j's. Rank of pj is constant. And this S lambda, the spectral surface, is just the projections up to k lambda. So that's usual. That is what I want to say is simply like that. If you take M0, 0, if you don't have the non-homogeneous term, then simply uj lambda is what you expect it to be. Uj lambda is exactly the open set away from the cone, so that where the jth eigenvalue is less than lambda. That's simple. So these are simple sets. Of course, we have to generalize in the case. It's surprising that actually the case that M00, just a constant matrix added to the symbol, adds a lot of difficulties, algebraic and otherwise, which you don't expect. But maybe a good analog is to think of the fact that the massless Dirac is very different from the massive Dirac in a certain sense. For example, you cannot combine them. There is a gap. Okay, also this notation has appeared throughout the week, so it is standard. L2S is the weighted space with weight S, any S real. HMS is the Sobolev version of that, that is with including M derivatives. And if you are talking about a real number, normally we are using just H sigma, namely without weight. We could add, of course, weighted with any sigma real, but we don't really need it sometimes. Most of the time. H minus ms is the dual space, and in particular there is a representation, a non-unique representation for example, for H minus 1s, which is a key space in this treatment. So in a non-unique way, you can represent it as such a combination of derivatives of L2S functions. Here is a theorem. It's the one and only theorem that I present here in detail. So bear with me for this. So you take, and even for this, I'm presenting it only in the constant coefficient case, and I'll comment on perturbations. So you take the constant coefficient operator, and you take sigma L0, its spectrum. So L0 satisfies the limiting absorption principle in the interior of each spectrum. The whole spectrum, of course, is continuous in this case. More precisely, take S bigger than 1 and consider the resolvent away from the spectrum, away from the real axis, as a bounded operator from L2S to L2 minus S. Of course, it is bounded L2 to L2, so L2S to L2 minus S. For S, any S positive is, of course, triviality. Then, the first thing is that this resolvent is bounded with respect to the H minus 1s norm, which is a statement about the differential inequality. It means that you take a solution of this problem and you can estimate with respect to a norm which is weaker, actually. Now, by the density of L2s in H minus 1s, you really can get that R0 is, in general, can be extended to a bounded operator. This is my notation for bounded operators. A bounded operator from H minus 1s to L2 minus s. Secondly, and this is the part which is normally called the limiting absorption principle, this operator valued function z to r naught z in this operator space can be extended continuously from the upper or lower half planes into the onto the spectrum. That is the union of either the upper, these are two statements, from up or from below, union with WW is the interior of sigma of the spectrum minus that finite set of selected troublemakers, of points that are bad, critical values, actually. So it can be extended continuously. And the notation that we're using is this. Limiting absorption actually appeared already in Tomir's talk and in other talks, I think. And of course, the result is that the spectrum is absolutely continuous in such open intervals, which is not surprising at this point. Okay, so this is sort of the basic structure, the basic theorem for limiting absorption principle. Why limiting absorption principle, which did not appear often in this during this week? Because limiting absorption principle, first known actually by physicists as the limiting amplitude principle, for good reasons actually. But limiting absorption principle is essential tool for everything, for perturbations, scattering, eigenfunction expansions. If you want to be specific, the way that to interpret mathematically the Lippmann-Schwinger equation for distorted eigenfunctions goes through limiting absorption, of course, and so on. The definition, actually the definition of scattering matrix is by limiting absorption. Of course, inverse spectral theory and an application that is not written here and actually to which I devote the last minutes of this talk is space-time regularity, global regularity of operators, for which the limiting absorption principle plays an important role. So it is sort of everywhere in this spectral theory of operators. And I'll just give a background. It's too much. And I have, at the end, maybe transparencies, if you want to. The history of limiting absorption principle is long and sometimes debated and so on. But let me just take the one that is of interest here in this talk. It is, so the background just for limiting absorption principle for Dirac and first order systems. If you take massive Dirac, so the first proof of the limiting absorption principle was done by Yamada. Next year will be 40 years, he's here. And then it seems that this is a topic that gets rediscovered every so many years. You know, so another proof is Jensen-Kato in a paper that was mentioned, 79, and then Balslev-Helfer in 92. And what is common to all of them, roughly different methods maybe, but what was common is the fact that they all use the fact that the square is the minus Laplacian. This was essential in somehow in the proof. They used more heavily the W, what I said, what Heisen for the FWT transformation, and they needed details for that, sometimes maybe unnecessary details. Homogeneous uniformly propagative, remember this has no cone of singular points. So this was done by Tamura in 1981 using pseudo-differential techniques. And the homogeneous strongly propagative by Wader 1985 in the paper that I mentioned in the beginning. He used, for this, he used eigenfunction expansions. Very detailed study of eigen by using polar coordinates on these slowness surfaces. Surprisingly, for unless you come up, I mean, I'm here to report my ignorance or something, unless you come up with some information, the non-homogeneous systems in general, so which include elasticity with background, say things, I mean, all the classical physics with some background, what do you call it, hysteresis and things like that, there is none in this respect. Nothing. And then you're talking about, you know, various, even absolute continuity is not known. Four, I mean, once you add perturbations. So, and of course, so this is, I mean, the massive Dirac is of course non-homogeneous, but then by reduction to the square, to the Schrödinger, by squaring it, you go back to Schrödinger. Okay. So what I want to do is to give a general framework for the LAP that works for all these cases with various other structural assumptions that I'm wiping under the carpet, but this part will be based on an abstract treatment that I developed with the late Alan Devinatz years ago. And so this is a review article, Smooth Spectral Calculus, that appeared in a volume edited by Deimut Schulze and Ingo Witt, the Springer series. There are other abstract approaches. For example, by abstract, I mean something that goes within the general framework of functional analysis, not a particular differential operator and so on. So there is the famous commutator method Moore, goes back to Putnam, 1981. And then recently there is by Girard, by energy estimates, also some kind of a framework, abstract framework. So here it is. So we are in this abstract setting. And H is a self-adjoint operator in a Hilbert space H. RZ is the resolvent, E lambda is the spectral family. And you assume a structure that contains X as a continuous, densely embedded subspace of H. And then, of course, through the scalar product of H, X star, the dual becomes, canonically, H is canonically contained in the dual of X star. So, I mean, for concreteness, you always think of X as L2S with positive S. H is the L2. But other possibilities exist, for example, Bezov spaces that were used by Agman and Dermander already in this game. So we say that H satisfies the limiting absorption principle, as we saw before in the concrete case, if the limits of the resolvents exist in this uniform or operator topology of X to X star, which would mean L2S into L2 minus S. Okay, so this is limiting absorption, and here is another definition. So you take an open set, a real open set, and you take any alpha bigger than 0 and less than or equal to 1, and you say that H is of type X, X star, alpha U, if there exists an A lambda in B X X star such that the weak derivative of the spectral family is A lambda, so this is just a notation for the weak derivative, acting on selected elements in the more restricted space X. And secondly, that A lambda minus A mu is that it is locally Helder continuous, in short, in the uniform operator topology. That's all. So that you have a weak derivative of the spectral family, which is Helder continuous. Theorem: if H is of type X, X star, alpha U, then it satisfies the limiting absorption principle in U, and the whole proof is in this line. You write RZ as the Cauchy type integral, that is dE lambda over lambda minus Z. dE lambda is A lambda D lambda over lambda minus Z. You realize, for physicists, as we say here, it's enough. But I mean, we need to regularize. But this is, everybody has their favorite ways of looking. Either it is those coming from complex variables. It's the fact that the conjugate function of a C alpha function is a C alpha function. For example, Helder continuous is or otherwise it's the Cauchy type, or a sort of a Hilbert transform of a Helder continuous function is a Helder continuous function. So we definitely need Helder continuity. So that's the whole proof, and we have therefore, which means that by the Privalov-Korn theorem, a nice proof actually of this theorem is to be found in an appendix in Courant-Hilbert. They use it in the analytic treatment of elliptic operators. Okay. So then you can go down with Z down to the real axis in the same family. So not only that you get the limiting absorption, but you get the fact, which is not obtained by all the other methods, that the values, the limiting values of the resolvent are Helder continuous automatically by this theorem. Now this is important because those values, for example, limiting values, are exactly the values that you will be using to study regularity of the eigenfunctions, distorted eigenfunctions, which is still by and large an open problem. How regular are the eigenfunctions, even for the Laplacian, by the way, perturbations. How regular they are with respect to the energy parameter, to lambda, to the spectral parameter. Of course, with respect to x, they are just what you get by ellipticity, by elliptic theory. Okay, so because it is so simple, you say, okay, so you make a definition, the usual thing about mathematics, you make a definition and then you have a theorem. And, but the point is that actually you can actually use this definition as I'll show in a minute. A lambda is called density of states in physics literature, for example, in Tanuji Cohen. It's not far from Morozov's point of view, the same definition, and the n lambda is very close to this thing. That is, the derivative is exactly the weak derivative here for periodic potentials. So density of states, and sometimes it is called also spectral density or terms like this. For example, the physicists sometimes implicitly study this density of states when in perturbation theory. For example, if you take the Stark effect, then the Stark effect, you apply whatever weak electric field, then immediately you have absolutely no point spectrum. And then you add this Coulomb potential. It is now the Coulomb potential is then a perturbation over the whatever weak electric field that you have, which is long range. And then by second perturbation theory is exactly finding the spectral density. You pretend that these are eigenstates, but there are no eigenstates. I mean, they are just long-living quasi-eigenvalues. Anyways, so the second point is that if H satisfies the limiting absorption principle, it does not mean that FH satisfies limiting absorption principle, even for FH, which is a square of H. This is interesting, and it is still open. I mean, if you want an exercise in abstract analysis, that is, what are the minimal conditions to allow that? This is why people working and going from Dirac operator, I'm talking, say, about the constant coefficient, Dirac, squaring it, getting a limiting absorption for the Schrödinger operator, which exists since the times of Agmon and Aidus, still have to do some work to go back. It is not given, it is not guaranteed. But in this case, if you have a type XX star, then it is automatically that FH is of the same type. This applies in particular, of course, for the case of the square root of the minus Laplacian. So I'm going back to that. Minus Laplacian would be limiting absorption principle exactly because of this observation. And what I'll not talk today is the fact that the abstract framework can be extended to H plus V, where V is short range. So to the Dirac, you can add a magnetic field with various smallness assumptions and short range assumptions. I use this point to advertise the fourth thing. There are no good abstract theory for long range perturbations. That is, short range you can define in an abstract way, nothing to do with decay at infinity or anything which is concrete, for the better and for the worse. But long range is not so easy to make a generalized statement.
What about the Moore theory, which can be formulated abstractly and it applies to long range perturbations?
Moore theory actually has no built-in perturbation argument in some sense. That is, it is all, you take the whole H, and then if you find this H to be in the commutator, then you're lucky. And of course, the long range in a concrete case, Coulomb potential or something like that, you know how to use the generator of dilations to make it also work in this case. It is a built-in theory which has no perturbation part to it in some sense. This is true also for Girard's recent, I think, same remark. Okay, so I remind you that this is that this is L2S and the norm is this. Here's a trace lemma. You take F hat in HS, S say bigger than a half and less than 3/2, then for any R, for any radius, you have an estimate for the trace which can be expressed like that. That is, now let's see. The fact that you have a trace lemma is known. You have a nice surface, compact surface, then you have a trace. If you're in HS, notice that it is HS with respect to F hat, which means with respect to L2S norm in the original F. So the fact that there is trace is the classical trace lemma. Two facts are here. The fact is that whatever sphere you take, whatever radius, this is bounded, the trace norm is bounded. You don't have, so this is not trivial, not self-evident, but it's true. Furthermore, if you go down to 0 with R, then since S is bigger than 1/2, you actually, the trace actually shrinks to 0 in this case. To do this, you need actually, one of the ways, the way we did it was to use a fractional Hardy inequality. That is that if you take any HS and divide, you see you divide by the same power of CS. Hardy would be that S is equal to 1, right? You get something which is bounded. The first proof I know of is a proof of Herbst, and I think and Rupert Frank had a nice simplification for that, right? That otherwise you lose an epsilon here, but so just to mention that it is related to Hardy type inequalities. Now the spectral derivative A lambda is connected to the slowness surfaces. That is, if you have those slowness surfaces, I remind you these are these, and the limiting absorption principle is treated by the trace lemma. And this is the point that I promised to be. I'm not going to be more detailed than that, but you see, if you treat in the usual classical by now Fourier integral approach, this is the hardcore Fourier integral approach to hyperbolic systems, right? And then you are faced with integrals like that, and your bread and butter is exactly where lambda JXC becomes bad, where you cannot treat by standard stationary phase arguments and so on. And this is why you have to treat case by case, you know, if you have cubic, if you have folds, if you have cusps of those surfaces. So this is the end of my mention of these methods, oscillatory integral approaches to this. But these are the only approaches that I know of that exist for systems, actually, by and large. Okay, back to the massive Dirac operator. You take, remember, we had this expression for the spectral family, and so you can differentiate the spectral family actually easily. You differentiate the spectral family, and you get, I took lambda bigger than 0, so only this place, only the upper two-spinor plays a role, and so it is this, you get a surface integral, and the surface integral is just the two components of GF. And then, since this is less than the full thing, you get by the trace lemma, again, you see the fact that I need to compensate. I get downstairs, I get something like this, so I compensate by this decay, by shrinking S lambda approaches M, in this case, the threshold, the bottom. And I get this expression for AM. This I write already as a pairing, AM lambda F, this wedge pairing is between L2 minus S and L2 S. So this means that AM lambda is uniformly bounded and uniformly Helder continuous, because these are statements about the trace, and they are easy. And in the uniformly Helder continuous in the uniform operator topology of this by the trace thing. And that's the end of the limiting absorption principle. So you get this for the Dirac immediately. And you see, you don't need, because you have this trivial inequality, means that you don't have to study the FWT transformation in any detail. You're done like that very easily, and you get this. And what I chose to do, again, as I said, everything that I'll say from now is relevant also to Dirac. I mean, it can be copied with certain technical assumptions to Dirac and to perturbations of Dirac. But I chose, for the fun of it, to bring and to sort of, in some sense, to extend the treatment and to say, okay, it is classical physics, you take the Klein-Gordon equation and you want to get estimates. So first of all, the Klein-Gordon is the same as the previous slide. You differentiate the spectral measure and you again get exactly the same thing. So, which is equivalent to the fact that Dirac operator of the square is exactly this. So there is no surprise in that, but the fact that you immediately get, for this operator, you get a limited absorption principle. So I repeated it, the trace lemma actually applies this, and so B satisfies the limiting absorption principle. Now that there are all kinds of games, like in Tomia's talk, S bigger than a half is good for internal limiting absorption principle. If you want to wash through the thresholds, you need to increase your S. This is a well-known property that you lose resonances. Resonances do not exist when you have a better weight. This is the statement. Okay, so, and then you can go even further. I mean, if you are in Klein-Gordon, why not visit also the wave equation by putting m equal to 0? And then it brings you to the wave equation with the same methods and the same approach. So for the classical wave equation, you have this. This is the classical wave equation. And there is a famous estimate by Kathleen Morowitz that is like that. This is sort of almost the Lorentz invariant measure, not the energy. And so it says something like, you can look at it as a Hardy inequality or a regularity statement for solutions of the classical wave equation, namely that you can divide the u squared by x cubed and still get something if you integrate over space-time. Now we are leading towards space-time. You still get something which is controlled by the H1 norm of the initial data. Okay, so the H1 norm is preserved. This is energy preservation, right? So even though you have H1, you can do better for almost every t. Not divide by x squared, but actually by x cubed. And so it is sort of a generalized or an improved Hardy inequality. By the way, compare it, and I'm not going into that, and I see the clock, to the Strichhartz estimates. This is the equivalent, the L2, weighted L2 equivalent of the Strichhartz estimates. Not to be interesting. But this was true only for 4, and then using the methods that I described before, that you can get for n bigger than 3, so concentrate on the case 3. Yes, on the case 3, you have this for any alpha which is between 0 and 1 strictly. So if you take alpha equal to 1, you will get the Morowitz thing, which is incorrect. But if you take, for example, alpha equal to 1/2, so take alpha equal to 1/2, here you get exactly here the Hardy integral, that is the u squared over x squared. But then you get the exact Lorentz invariant, that is the Lorentz invariant with alpha equal to 1/2, that is the h1/2 norm. So you get for almost every t, you get Hardy behavior, but without Hardy assumptions, actually. So this is regularization by the wave equation. All this has analogs in the case of the Dirac and the Klein-Gordon equations. And so global weighted L2 space-time estimates for Schrödinger operators are, of course, by now, since 15 or 20 years, are well known. And in fact, the famous addition of 1/2 derivative that follows from these things, it was first done by that. But for Dirac operators, it's pretty recent. So using exactly the special form of the Dirac operator and things like that, it was done by Boussaid in 2006. I mean various space-time estimates, global estimates of the kind that we saw for the wave equation, and by D'Ancona Fanelli in 2008. And what I wanted to do in the last 2 minutes, is to illustrate this via Klein-Gordon. So, but again, I mean, the fact is that you have the Klein-Gordon equation, and the same thing will work for Dirac. And as I said, the same thing will work with perturbations, given the right amount of assumptions on these perturbations. So for the Klein-Gordon, you take this Cauchy data and you write a solution. You decompose the solution, and you are back, of course, to the symbol that we all saw all the time, the square root, the so-called relativistic Schrödinger, it was called by some, relativistic Schrödinger operator, like that. And then you have the following theorem. The theorem says that take this, and then you have, for the Klein-Gordon, you have this estimate in space-time. That is, if you take a certain weight function, your solution will sort of, at a measured way, will escape every cone in space-time. And this is expressed by the fact that you have here, this is actually the L2 norm I chose to do, b minus 1, b is, say, m is bigger than 0. You can take either, but if m is bigger than 0, then this is a bounded operator, and then you have actually an L2 energy norm for both the initial data and the initial, that is the initial U0 and V0. Okay, so, and the proof is, I was planning on having enough time for that, but I don't. The proof consists of actually using in a simple but efficient way the spectral derivative, the density of states. Let me just point out the following facts. So the essential thing is here, and is in some sense, you develop a spectral calculus for A lambda. This is what I call spectral or a smooth spectral calculus. You simply replace everything by Plancherel integrals, and then it is immediate. The proof takes one more page. But the fact that you can do all this relies on two things. First of all, that A lambda has the Cauchy-Schwarz property. I mean, either you look at it, it is the derivative of an increasing function, E lambda, right? So it's a monotone increasing, so the derivative is positive. Or if you don't like it in the concrete case, A lambda was just an L2 product on some surface. So it is just another L2 scalar product, a trace product or something. So you have the Cauchy-Schwarz. And secondly, A lambda decays at a certain rate. We didn't discuss this, and in fact, in the Dirac case, it is only bounded and does not decay at infinity. But if it decays at a slow rate, lambda to the minus a half, say, for the Schrödinger operator. Which means that the lambda to the minus half decay is good news because it means that you can add regularity. This is the famous 1/2 derivative that can be added to the regularization of Schrödinger solutions. On the other hand, it is bad news for integrability. I mean, lambda minus a half does not lead you anywhere, and this is just washing the classical, the Fourier integral treatments, where actually you look individually at every direction. And then if you look at every direction, you have a decay which is dictated by the bad points. So you don't get more than that, of course. By the caustics or the faults or whatever, it happens to be geometrically. But we know we have this spectral theorem, the same theorem that was referred this morning as the von Neumann, Stone von Neumann, the famous spectral theorem. I mean, this is a derivative, so it integrates out to be f squared. So there is no doubt that here you can use it. So it gives you a better property, and that's exactly the other key ingredient that you need. So just two simple ingredients. And this is the proof, but okay, you can read it through the proof, and I see Maria is already threatening. I'm the last one, yes. Okay, so thank you very much.
Questions?
Your equation 27. We'll go back 2 slides back.
I don't remember what was it.
Yeah, no, one more. Yeah, this one.
27.
Yeah, that's right. So if alpha is equal to 1, then of course equation inequality 27 is not true. But can you improve it? Can you prove it by introducing a log term, logarithmic term?
Wow, what a question! It's I and other people, we spent a long time on that. Yes, it is. It will be exactly the equivalent of adding the next term to the Hardy inequality. By the way, there is a Hardy inequality by these lines also to the Dirac, but not with the V that you are using in the work with Loss and Vega, because it's a Coulomb. So for Coulomb, we're not. But here to add, this is an open thing, and in fact, when I was Quran 3 years ago, I discussed it with Kathleen, but she doesn't remember it anymore. Her work was in the 70s. She said, I don't know, but she liked the fact that you have something for three-dimensional thing, but she said, and it is not, by the way, I don't know if there are any examples. This is the weakness of all this. I'm not sure there is any example to show that it is not true with alpha equal to 1. Only that the method that we're using is unable to produce that, and she was unable to produce that. But it's all this I regard as Hardy inequalities averaged on time, in some moral sense.
Other questions?
I remember your interesting paper on the smoothing effect. So if it would be nicer if you spoke on your paper on the smoothing effect.
No? If Maria allows me for. Yeah, But of course, because of your beautiful results, there is no smoothing for Dirac. So if we are focused on Dirac, it is not, and I don't know still we are at, some of this is a work in progress, so we still don't know what is happening and what kind of global regularity. We get global regularity Dirac along the lines of wave equation, so there is some regularity. But what is the best regularization in space-time? We don't know. We have to work more. But, yes.
Other questions? Okay, no, thank you very much again.